can ultimately end up in glucose, and I'm going to show you some pathways for that. And then there's amino acids. And starting with, let's look at gluconeogenesis. So there are three irreversible reactions in gluconeogenesis. Hexokinase is not reversible. PFK, phosphorylated kinase 1 is not reversible, and pyruvate kinase is not reversible. So we have to find ways around that. So yesterday we said, well, let's deal with the high protein diet. Let's just start with that as our example, and deal with a variety of different gluconeogenesis. So we start with allergy. And we'll look at this toward the end of the quarter. We can deaminate that easily. So we'll deaminate it negative. One of the big things that alanine does, it's going to pack nitrogen, amine groups, out of the muscle. So alanine is going to be synthesized in the muscle from pyruvate. It's going to go to the blood and then head for the liver. In the liver, it does two things. It's going to be deaminated, and we're going to use that nitrogen more than likely for the urea cycle, because we've got excess nitrogen now that we're trying to pack out in the muscle. We'll talk about why. And then the second thing is we end up with pyruvate. And so our pyruvate is going to be used for gluconeogenesis. So let's look at that system. So here we are with pyruvate. Now, pyruvate kinase is not reversible. So what we've got to do is dump this thing into the mitochondria. And based on, I think I said yesterday, based on how you want to do your accounting, you can either charge yourself a 0.27 of an ATP for that proton that goes in with it, or you can play with protons and figure out whether or not you think it's worthwhile. I will charge until this year, and we're working on a paper right now on protons, protons. And really that proton that goes in, I think, arises, and you go from glucose to pyruvate. So it's already there. It's not like it's a proton read. So I'm not sure I charge, but we get our pyruvate into the mitochondria. In the mitochondria, two things can happen with that pyruvate. One is it can go to acetyl-CoA with pyruvate dehydrogenase, which is highly regulated. Two is that we could use pyruvate carboxylase and convert it to OAA. So we can take the pyruvate, and in the presence of ATP to an ADP, and we get an inorganic phosphate off of that, and activated CO2, which is going to come in as bicarb. We're going to put, and let's put a C14 on that. Let's label that sucker so we know where it is. We're going to end up with OAA. Now, OAA can't get across the mitochondrial membrane. There are three possible ways to get that carbon skeleton out of the mitochondria. And really, it's going to depend upon what's the precursor for alanine. We're using protein. So alanine is our precursor. It could be lactate. It could be the corycyte. It could be anaerobic, the result of anaerobic metabolism. Well, and then you get lactate in the blood. It's pulling the lactate out of the blood. And that lactate then is converted to pyruvate in the cytosols in the liver. We'll look at that. There are three possible ways to get that sucker out of there. One, in the human, you have PepCK in both the cytosol and the mitochondria. You could convert this to PEP with PepCK. And PEP, phosphonylpyruvate, can go across that mitochondrial membrane. You could, thinking about the malate aspartate family, you could convert it to aspartic acid, and aspartic acid can get across. Or you could convert it to malate and shove it out as malate. So we have three possible ways. If you have PepCK in the mitochondria. Not every species has PepCK in the mitochondria. We'll talk about that. We are going to toss it out as malate. So we're going to take malate dehydrogenase, And we're going to reduce down, we're going to reduce our OAA. That's a reversible enzyme. We're going to reduce our OAA and make malate out of it. And the malate, of course, would go across the mitochondrial membrane. So let's get malate. And the malate is going to get out. Still got that thing. So malate just left. So mitochondria, cytosol, cytosol. The malate, we already got the structure, so this malate in the cytosol, in the presence of malate dehydrogenase. You're going to take an NAD to an NADH. And we're going to get back our OAA. PepCK. And this is, I think I said before, this is the enzyme that really got nutritionists all excited about nutrition and gene expression. Case Western Reserve Biochemistry Department demonstrated that. PepCK as an enzyme, the total amount of it goes up. The amount of that PepCK in the liver goes up on the ketogenic diet. So they started thinking about nutrition and gene expression, what nutrition might do to gene expression. And of course, that shouldn't surprise anybody if you think about alcohol dehydrogenase. Huh? Yeah, carbon still more. PepCK is going to require some GTP. So that's an ATP equivalent. So we've got a GTP going to a GDP. We're going to drop off the CO2. That CO2 that comes off was the one that we put on with the 5-carb way back here where we used the pyruvate carboxylase. So this is going to allow us to convert that back to PEP. So we've got PEP out of the deal. And PEP is going to go back up the pathway. Like it's going to just be the reverse glycolysis program. So there's PEP, and since you already know the structures, and this is why we didn't have you draw all the structures on midterm 3. They have to draw them out for glycolysis, for gluconeogenesis, so it didn't seem fair to make you do it twice. I'm a real principal guy. Enolase. So we're just going to go backwards. Enolase, put in some H2O, and we're going to, we'll get 2-phosphoglycerate out of the deal. Phosphoglycerate. The 2-phosphoglycerate, something wrong with that. I got it on here. H2O. 2-phosphoglycerate with the reversible enzyme 2-phosphoglycerate mutase, reversible reaction. Phosphoglycerate mutase. We're going to make 3-phosphoglycerate. 3-phosphoglycerate, glycerate kinase. Glycerate kinase, we have 1,3-bis-phosphoglycerate. Bear in mind that that's a reversible substrate-level phosphorylation. That's going to cost another ATP. Bis-phosphoglycerate. Bis-phosphoglycerate. And it's this step that determines how you get your oxaloacetate out of the mitochondria. In this case, we came out as OAA because we used protein, and this is the glyceraldehyde 3-phosphate dehydrogenase, and we're going to need to take an NADH. So you got about 2.7 ATPs worth of NADH to an NAD. You're going to drop off that inorganic phosphate, so that comes off, and now we have glyceraldehyde 3-phosphate. Glyceraldehyde 3-phosphate. Well, if we're headed for glucose, some of this has got to be converted to dihydroxyacetone phosphate. So we have a phosphate isomerase. So we have DHAP. We can take the glyceraldehyde phosphate, DHAP with aldolase, reversible reaction.
Question?
Yep.
That second to last structure, what is that?
This one?
Yes.
Glyceraldehyde 3-phosphate. Aldehyde 3-phosphate. Glyceraldehyde 3-phosphate. Take both of these. This is why I like the board to roll up rather than side to side. You're lucky I ain't erasing this as fast as I'm putting it up. That's what they did when I took 5 years. All right. This board or this board?
Okay, the one you guys handle, can you label those? Yes.
Well, this is 2-phosphoglycerate. See? You should look at stuff and figure it out. 2-phospho.
Yeah, I lost it.
Well, it ain't an aldehyde. It's an acid, so it's glycerate. This is a mutase, still an acid. Now it's a 3-phospho, so it's 3-phosphoglycerate. You're supposed to know this from last board. Is that the board you want? Very good. No problem. Reversible reaction. Aldolase, phosphate isomerase. We're going to get fructose 1,6-bisphosphate. Fructose 2,6-bisphosphate. So fructose 2,6-1,6. 2,6 is going to be important in a minute. Fructose 1,6-bisphosphate. H. K is not reversible, so it's going to require that we use fructose 1,6 is phosphatase. That's going to cleave off an inorganic phosphate. There's no substrate level phosphorylation on this. That gives us fructose 6-phosphate. I have to draw it out, I suppose. So there's fructose 6-phosphate. Could ask you if it's alpha or beta form. I'll do that on the exam. Fructose 6. We have that with a reversible enzyme, the phosphoglucoisomerase is going to convert it to glucose 6-phosphate. Hexokinase is not reversible, so we're going to put that thing into the endoplasmic reticulum, so the transport system takes it into the endoplasmic reticulum. The glucose 6-phosphate in the endoplasmic reticulum. On the inside surface of the endoplasmic reticulum is glucose 6-phosphatase. You're missing that, that's glycogen-storage disease 1A, B, or C, or D, depending on which part's gone. Glucose 6-phosphatase, inorganic phosphate comes off. You have to read glucose, you've got to transport the glucose back out, and you've got to transport the phosphate back out of that endoplasmic reticulum, and then you've got free glucose. So that's considered another. Yeah?
What point is the donor in the phosphate?
Right here. That glucose 6-phosphatase is on the inner membrane of the endoplasmic reticulum. That diagram I showed you the other day. Yep. No, run that by me again. 6. What? To remove the phosphate off the fructose 1,6 to make fructose 6, we use fructose 1,6 phosphatase. Fructose 1,6 phosphatase, just so you know, is also PFK. It just depends on whether it's phosphorylated or not. So we'll have to deal with that. So, here are the points. Number of points you've got to consider. First of all, it's expensive. We started with alanine. Because we started with alanine, we are going to transport that carbon skeleton of alanine out of the mitochondria as malate. And you'll see why in a minute. So let's do a little accounting here. Pyruvate carboxylase, phosphorus and ATP. The malate dehydrogenase, phosphorus and NADH. That's an NADH in the mitochondria. So malate dehydrogenase, mitochondrial, minus an NADH. So we'll have to go back to the last quarter to figure out what an NADH is with inside the solvent of the mitochondria. We're pretty good. That gives us malate. Malate goes out. And once we get the malate out of the mitochondria, in the presence of malate dehydrogenase, we make NADH. That's important. This is important. That's why we're transporting our moving carbon skeleton out of the mitochondria as OAA if we start with alanine or protein. If we start with lactate, we aren't going to do this. But we have to if we start with alanine, because what's happening out here in the cytosol is you're starting to build up the NADH. You are increasing the NADH to NAD ratio. Okay, so...
Are you still down limited NADH?
No, right here, malate dehydrogenase, cytosol, plus 1 NADH. So you've made one. Wow.
What did you say? Only opposites instead of alanine?
We're only going to, we transport pyruvate, which is our gluconeogenic precursor in this case, out of the mitochondria as malate. We could do it as PEP, as PEP, or we could do it as aspartic acid. We can take that OAA and then in the mitochondria convert it to PEP, because some of us have PEP-CK in the mitochondria, and it'll transport out. Or we could convert the oxaloacetate to aspartic acid and it'll go across. We didn't do that. In this case, we converted and if we use lactate, if I put lactate up here, we're going to transport out that pyruvate that comes off the lactate from lactate dehydrogenase. That's going to come out of the mitochondria either as PEP or as aspartic acid. But here's why. Don't memorize this stuff. Think about the pattern. We have, by bringing it out as malate, we have to convert it back to oxaloacetate because that's the precursor that, of PEP, for PEP-CK. That's your substrate for PEP-CK. In making that OAA out here in the cytosol, we are increasing the NADH to NAD ratio. And by now you should have a good feel for the fact that when you change that ratio, it has regulatory effects. All right. So we got ourselves that. We're going to have to charge ourselves with GTP for the PEP-CK. If you do it for mitochondria, same issue. It's going to cost you GTP. Some subtle difference though in the value though, isn't there? If you're using that GTP, making the GTP in the mitochondria, you haven't got to charge yourself that proton to get the GTP out and the GTP and the organic phosphate back in. So it's a more efficient use, if you will. So PEP-CK costs us a GTP. Alright, now where are we? So we got PEP, we got 2-phosphoglycerate, we got 3-phosphoglycerate, we got glycerate kinase, to make 1,3-bis-phosphoglycerate. That costs us an ATP. Glycerate kinase. Minus an ATP. Got 1,3-bis-phosphoglycerate somewhere in this disaster. Hello. 1,3-bis-phosphoglycerate. And here's why. If your substrate is an amino acid, you're probably going to pump it out as malate. So if we make alanine or pyruvate, it goes into the mitochondria, we make oxaloacetate out of it. If that oxaloacetate is coming from carbon skeletons that represent protein, we're going to have to send that out as malate. And here's why. Because now we need NADH. And the malate dehydrogenase has allowed us to increase the NADH to NAD ratio. So we have a cytosolic NADH to make this reaction go forward. So right here, glyceraldehyde, 3-phosphate dehydrogenase, that's going to use that NADH that we got out of malate dehydrogenase in the cytosol. Still costs us an NADH in the mitochondria, but basically what you're doing is a reverse